Black holes are not just the strangest objects in the universe. They are the sharpest tests we have of how reality actually works. They are places where nature stops being polite, where the rules we trust are pushed until they fracture, overlap, or contradict one another. A black hole is not merely an object, it is a question carved into space-time itself. They form when mass is compressed beyond a critical limit, when gravity overwhelms every known force that might resist it. But their importance goes far beyond the mechanics of their birth. Black holes are the most extreme laboratories the universe has ever built, forcing general relativity and quantum mechanics into direct confrontation. These are the two pillars of modern physics, each staggeringly successful in its own domain, and each catastrophically incompatible with the other. Black holes are where that incompatibility becomes unavoidable. In this long exploration, we look back across years of discoveries and ideas to understand how black holes form, how they evolve, and why they may ultimately teach us how to reconcile our deepest theories of reality. To understand black holes is to understand the limits of what we know. At first, black holes were little more than mathematical curiosities. They emerged naturally from Einstein's equations of general relativity, but that alone did not guarantee their existence. Physics has a long history of elegant mathematics that never manifests in the real universe. Just because an equation allows something does not mean nature uses it. For decades, black holes lived in this uncomfortable space between mathematics and reality. That changed. Today, there is no serious doubt that black holes are real. We see their gravitational influence shaping stars, ripping matter into glowing disks, launching relativistic jets, and warping space-time itself. We hear them collide through gravitational waves that ripple across the universe. Black holes are no longer theoretical, they are astrophysical facts. But to actually make a black hole, Einstein's descriptions of mass, energy, and spacetime are not enough. Gravity alone cannot tell the full story. To understand how matter resists collapse and how that resistance ultimately fails, we must invoke quantum mechanics. If you are willing to follow the physics all the way down, we can build a black hole step by step. Start with a very massive star and wait. Massive stars live fast and die young. They burn through their nuclear fuel at an extraordinary rate, fusing lighter elements into heavier ones in their cores. For millions of years, this fusion produces enough outward pressure to balance gravity. But that balance is temporary. As the star ages, fusion progresses through heavier and heavier elements, forming layered shells like a cosmic onion. Hydrogen fuses to helium, helium to carbon, carbon to oxygen, oxygen to silicon. Each layer burns hotter and faster than the one before. Eventually, the star produces iron in its core, and that is the end. Iron is a dead end for fusion. Fusing iron absorbs energy instead of releasing it. Once the core becomes iron, the star loses its primary source of pressure. Gravity wins. The core collapses catastrophically. Electrons are crushed into protons, forming neutrons and neutrinos in a violent cascade. The outer layers rebound off the collapsing core in a supernova explosion that can briefly outshine an entire galaxy. Heavy elements forged in that moment are flung into space, seeding future stars, planets, and life. What remains is the core, a neutron star. A neutron star is one of the strangest objects in the universe. It packs more mass than the sun into a sphere the size of a city. Its density rivals that of an atomic nucleus. A teaspoon of neutron star material would outweigh a mountain. Gravity on its surface is so intense that spacetime itself is deeply curved. Clocks run slower. Light struggles to escape. Beneath a thin crust of iron plasma, a neutron star is a quantum mechanical object. Its very existence depends on quantum laws, and it is quantum mechanics that both saves it from collapse and ultimately allows us to destroy it. To understand why, we need to stop thinking in ordinary three-dimensional space and start thinking in quantum phase space. This is a six-dimensional space that includes both position and momentum. Every particle occupies a volume in this space, and the rules governing that occupation determine whether matter can resist compression. Two principles dominate this regime: the Pauli exclusion principle and the Heisenberg uncertainty principle. The Pauli exclusion principle states that no two fermions can occupy the same quantum state. Neutrons are fermions. In a neutron star, phase space is packed. Every allowed position and momentum state is filled. This creates degeneracy pressure, a quantum resistance to further compression. It is not a force in the traditional sense. It is a consequence of forbidden states. Degeneracy pressure is immensely powerful. It can resist gravity even under the extreme conditions of a neutron star. As far as we know, the Pauli exclusion principle cannot be violated. You cannot push two fermions into the same quantum state. But nature finds another way. The Heisenberg uncertainty principle tells us that position and momentum cannot both be precisely defined. If you squeeze particles into a smaller region of space, their momentum becomes increasingly uncertain. That uncertainty translates into enormous particle velocities. As a neutron star gains mass, its neutrons become more tightly confined in position space. Their momentum space expands. Phase space stretches. The star does not grow larger. It grows more energetic internally. Its radius shrinks. This is a quantum effect playing out on stellar scales. As mass increases, the neutron star becomes smaller, denser, and more curved. Clocks slow further. Space-time warps more violently. Beneath the surface, the conditions approach something truly extreme. There exists a critical mass where this balance fails. At about 3 times the mass of the Sun, the neutron star's radius becomes smaller than its Schwarzschild radius. The surface crosses a threshold. An event horizon forms. At that moment, the neutron star becomes a black hole. From the outside, something remarkable happens. The collapsing object appears to freeze at the event horizon. Its light redshifts and fades. Time seems to slow to a halt. The star goes dark. Inside, however, collapse continues. Space-time itself changes character. All possible paths forward in time point inward. Every trajectory leads inevitably to the center. The material inside is crushed beyond neutron degeneracy. Neutrons are torn apart into quarks and gluons. Those, too, are compressed further. Momentum grows without bound. Position collapses towards zero. General relativity predicts that all of this ends in a singularity, a point of infinite density and infinite curvature. Whether such a thing truly exists is unknown. Physics breaks down before we reach it. The singularity may be a sign not of physical reality, but of theoretical failure, a place where our equations stop making sense. From the perspective of the outside universe, the singularity never forms. It exists infinitely far in the future. The only thing that truly exists is the event horizon. Everything beyond it is causally disconnected from us. Black holes remember almost nothing about what formed them. From the outside, they are defined by just 3 quantities: mass, spin, and electric charge. All other information appears lost, and that creates a profound problem. Quantum mechanics insists that information cannot be destroyed, yet black holes seem to erase it. When they evaporate through Hawking radiation, that information appears to vanish forever. This is the black hole information paradox, and it strikes at the heart of physics. But Hawking radiation itself is an even deeper shock. In 1974, Stephen Hawking showed that black holes are not eternal. They emit radiation. They have temperature. They lose mass. They can evaporate completely. This radiation arises from the interaction between quantum fields and curved spacetime. Near the event horizon, the vacuum is distorted. The definition of empty space breaks down. What one observer sees as vacuum, another sees as particles. Hawking's calculation revealed that black holes glow faintly, emitting particles with a thermal spectrum. The smaller the black hole, the hotter it gets. The smallest black holes would evaporate explosively. This discovery forced physicists to confront the thermodynamics of black holes. Jacob Bekenstein had already realized something extraordinary. The surface area of a black hole's event horizon never decreases. This mirrors the behavior of entropy, which always increases. Bekenstein proposed that black holes have entropy proportional to their surface area. Hawking confirmed it. Using the temperature of Hawking radiation, he derived the exact entropy of a black hole. It is enormous. Black holes contain more entropy than any other objects in the universe. This led to a staggering conclusion. The maximum amount of information that can be stored in a region of space is proportional not to its volume, but to its surface area. This is the Bekenstein bound. Reality, it seems, is holographic. Everything inside a volume of space can be described by information encoded on its boundary. This idea underlies the holographic principle, one of the most powerful insights in modern theoretical physics. Black holes may be the key to understanding space-time itself as an emergent phenomenon. And then there are the strangest possibilities of all. Primordial black holes may have formed in the early universe from density fluctuations shortly after the Big Bang. Some may still exist today. They could even account for a portion of dark matter. White holes, the time-reversed counterparts of black holes, emerge naturally from the equations of general relativity. They expel matter instead of absorbing it. Whether they can exist physically remains unknown. Some speculate that the Big Bang itself resembles a white hole. Even entire universes may be born from black holes connected through wormholes, forming a cosmic family tree. These ideas remain speculative, but they are not nonsense. They arise directly from equations we trust, pushed to their limits. Black holes are not just objects in space. They are mirrors held up to our theories, reflecting both their power and their flaws. They show us where gravity and quantum mechanics collide, where information, entropy, time, and space blur into something deeper. To understand black holes is not merely to study collapsed stars. It is to study the architecture of reality itself, and we are only just beginning to look inside.